Hello, everyone, and many thanks for attending this talk. My name is Lennart Binkowski, and I'm very grateful to be given the opportunity to present to you our work at this year's IEEE Quantum Week. Without further ado, let's jump right into the presentation. So, this talk will be about the quantum tree generator and how it improves the QAOA state-of-the-art for the knapsack problem. Here you can see a picture of me and my three wonderful colleagues, all from Leibniz University, Hanover, where we developed the quantum tree generator, which is a state preparation method to generate all feasible solutions of the knapsack problem. Accordingly, we will cover that quantum tree generator, which is arguably the coolest part of this project, but later on. First, we will talk about the QAOA, something most of you are probably familiar with, but nevertheless, we will talk about the fundamentals, especially about feasibility preservation and the notion of convergence of QAOA. And of course, we also have to define the problem that we want to tackle, namely the knapsack problem. And since that's rather straightforward, we will start with this one. So the knapsack problem, very easy to explain, very elegant and simple formulation. We are given n items. Each of these items comes with a profit value Vm for the nth item and a weight Wm. In addition, we have some capacity C of our knapsack. The goal is now to pack items into our knapsack such that their cumulative profit is maximized, but under the constraint that their cumulative weight may not exceed the capacity C. Here's the corresponding problem formulation when we introduce binary decision variables xm. Xm equals 0 means we don't include the nth item into the knapsack. Therefore, its profit does not contribute to the cumulative profit, but also its weight does not contribute to the cumulative weight. Xm equals 1 means we pack the item actually in our knapsack, in which case both its profit and its weight contribute to this summation. Here's some facts about the knapsack problem. From a theoretical point of view, it's an NP-hard problem. However, in practice, it's rather easy to solve. State-of-the-art solver is Combo. That's a solver that's already like 26 years old. Nevertheless, still the best performing solver for this task, and it's based on dynamic programming. In addition, there are also very well-performing heuristics, so algorithms that don't give you the optimal solution in general, but a very good approximate and which run very, very fast. And one of them is the integer greedy method, which is so simple that it perfectly fits on the slide. So first we sort the items by descending quality. So by the ratio of their profit to their weight, such that then the first item has the highest quality. And then we simply go through all these sorted items one by one and check whether the current item still fits into the knapsack. If so, then we subtract its weight from the remaining capacity because we want to include it, and we add its profit to the total profit. Very simple. So if an item doesn't fit, we simply skip it and go on to the next one. By this, we favor these high quality items to be included. That does not give the optimum in general, because the runtime of this algorithm is n as soon as the items are sorted. So if this would give the optimal always, it would definitely not be an NP-hard problem. But nevertheless, in practice, those are already very good, very high quality solutions. So now, how do we tackle the knapsack problem with a quantum computer? We follow the very standard encoding formalism where we take bits and map them to qubits, and therefore taking bit strings of length n and map them to computational basis states of an n-qubit Hilbert space. The objective function we turn into an objective Hamiltonian diagonal in the computational basis, which maps each computational basis state to itself times the objective value its classical label has. And by this, it's immediately clear that some bit string x star maximizes the objective function f if and only if the corresponding computational basis state is in highest energy state of the objective Hamiltonian hf. However, we did not talk about constraints yet, which, however, is very important. Because for the knapsack, for example, if we simply leave out the constraints, we turn the problem into something very boring, namely the objective function f is always maximized by the all one bit string, right? If I just include all the items, I definitely maximize the profit. So that's a very boring problem. Therefore, we should definitely talk about how to incorporate these capacity constraints. In general, we have two options. We could either soft code the constraints, so introduce soft constraints to the objective function, and therefore to the objective Hamiltonian. And the idea here is to penalize infeasible solutions such that their objective value lies below the ones of the feasible solutions, or at least below the one of the optimal solution. Second option is to use hard constraints, where instead of altering the objective function, we enforce via other methods the search to be restricted to the feasible subspace, meaning the linear span of all the computational basis states whose label X is feasible. Let's first talk about the soft constraints. And for that, let's define a feasibility marker function G, which takes in bit strings of length n and outputs 1 if and only if such a bit string is feasible. Then in general, so not only for the knapsack problem, but really in general for any maximization problem, we can find some positive number alpha such that if I want to maximize f only over the feasible bit strings, this gives me the exact same set of maximizers as if I would maximize f minus alpha times 1 minus g over all the bit strings. Simply because if alpha is high enough and I take an infeasible solution, then 1 minus g equates to 1, right? G of x would be 0 for an infeasible solution. So 1 minus g of x is 1. And then it contributes with the number alpha. But since it's subtracted, this will lie below the optimal solution if alpha is large enough. Now, for optimization problems like the knapsack problem, where the function f only maps to positive numbers, I can actually get rid of this hyperparameter alpha and simply replace f by the function f times g. So in this case, if a bit string is infeasible, g of x is 0, therefore f times g applied to x is 0, which then lies below the optimum of f, which is some positive number if it's a non-trivial instance. So that's one way. The second way is to use hard constraints. Let's again keep the notion of this feasibility marker function G. But now instead we talk about a feasible subspace. I already introduced that 2 slides ago. Let's give it a name now. Let's call it S. And with this new notation for G, this simply means S is the linear span of all computational basis states such that G of X, where X is the label, equals to 1. And then we have also the notion of a feasibility preserving operator. So we call operator A feasibility preserving if it maps the feasible subspace to itself. And one very important example of such a feasibility preserving operator is the objective Hamiltonian H of F, right? It has the computational basis states as its eigenstates, especially the feasible ones. Therefore, it maps those feasible ones to themselves and therefore leaves the feasible subspace invariant. And now the simple fact holds that X star maximizes F under G, so under the constraints of our problems, if and only if the corresponding computational basis state is a highest energy state of HF restricted to S, which especially means, of course, that the computation base state itself lies within the feasible subspace. Okay, now that we have covered these two types of enforcing constraints, let's talk about an algorithmic scheme where we can actually implement both of these types, namely the quantum approximate optimization algorithm, which should be well known. It fundamentally relies on the Rayleigh-Ritz principle, which states that some state psi star is an highest energy state of a Hamiltonian HF, if and only if the expectation value of HF is maximized within that state psi star. So by this, we can translate the question of finding a highest energy state into a maximization task for the expectation value. That's something we can control way better because we have a concrete numerical quantity. The ingredients of the QAOA are some initial state, iota, and then two parameterized quantum circuits, UP of gamma, that's the phase separator, and gamma is some real parameter, and UM of beta, again, beta being a real parameter, where this is called the mixer. And then from these two parameterized quantum circuits, we can build up our parameterized triestates, which we simply name by their label beta gamma. And we do that by applying alternatingly these two circuits to the initial state iota. And then the final quantity that's interesting for us is the expectation value of our target Hamiltonian HF in those parameterized states. And we can simply name this capital F of beta and gamma. So this is a function now from the parameter space directly to the real numbers. And with this, we end up at our very simple algorithmic scheme. Why there's an improvement, we estimate first the value of f of beta and gamma by simply preparing these triestates several times and measuring them in the computational basis state. And then we feed that estimate for this expectation value to a classical optimizer, and it takes care now of updating the parameters beta and gamma. And with these new parameter values, we re-enter on the quantum computer, again prepare new triestates and continue the loop, so on and so forth. And then later on, the same ideas were generalized to the quantum alternating operator ansatz, so same acronym in the end, QAOA, but now also with the built-in notion for feasibility preservation. It's still based on the Rayleigh-Ritz principle, but this time we talk about the restriction of HF to the feasible subspace S, and the fact that the highest energy state of that restriction also maximizes the expectation value of HF over all the states within the feasible subspace. Then the components are the exact same ones as for the original QAOA, with the only difference is that the initial state iota is now required to also lie within the feasible subspace, and that both phase separator and mixer are required to be feasibility preserving. That means they map the feasible subspace to itself. But the trial states and also the expectation value function capital F are built exactly the same. And therefore also the algorithmic procedure is exactly the same as for the original QAOA. Together with their generalization of the QAOA, Hetfield et al. Also discussed mixing properties. So desired properties for the mixer of beta that it should have in order to translate between feasible computational basis states. Namely, what they imposed was that for any pair of feasible bit strings, x and y, there should be some power r and some parameter value beta, such that when applying the rth power of of beta to the ket y, there should be a non-zero overlap with the computational base state x. One can strengthen a bit this mixing property in order to then rigorously prove convergence of the QAOA. That's what we did in another work. It's a bit more complicated notion of mixing property, which requires two additional notions. The first one is the one of a coordinate subspace. And here we take any subset of the bit strings of length n, let's call that x, and then the span of x, which is by definition the linear span of all the computation basis states with label in that set x. This is called a coordinate subspace. And then one example of such a coordinate subspace is, of course, the feasible subspace, which is simply the span of the set of all bit strings which fulfill the constraints G, so on where the function G equates to 1. Furthermore, let's restrict the mixer to be a product of individually exponentiated Hamiltonians Hj. And then we demand that for all pair of feasible bit strings x and y, it should hold that the overlap of Hj applied to y with x should be bigger or equal than 0. Furthermore, if for all Hj from our set of Hamiltonians, it holds that they map some coordinate subspace span x to itself, then it should already follow that x is either the empty set, which means the span would be the 0 space, or x is the whole feasible subset, which means x is the set where G equates to 1. And then indeed, this is a stronger requirement. So this implies the notion of mixing properties given by Hetfield et al. But what is nice about this mixing property is that indeed one can rigorously prove convergence of the QAOA, which means it can approximate the optimum arbitrarily well with sufficiently many layers. So if I include sufficiently many parameters and pick the right values for these parameters, then I'm guaranteed to come as close as I want to the optimal solution. Now that we have discussed the possible convergence of QAOA, let's discuss a framework which often offers this notion of convergence, which is the Grover-Mixer QAOA, which was also presented at IEEE Quantum Week 5 years ago, and which has as its main idea to retrace the mixer design to the design of a state preparation circuit for all feasible states. Let's assume we already have constructed a unitary U-Grover SP, which takes in which maps the zero state to the uniform superposition of all feasible computation basis states. So I denote this with this ket of G equals 1. Then we can turn this into a QAOA mixer simply by defining the mixer to be e to the minus I beta times the projection onto that uniform superposition state. And then if you just plug in how the state arises from the state preparation circuit, we simply get that this Grover mixer can be written as the identity minus 1 minus e to the minus I beta times the projection onto the zero state sandwiched between this state preparation circuit. And then the Grover mixer QAOA simply consists of first applying that state preparation circuit to the all zero state to get that uniform superposition of all feasible computational basis states, and then to apply the QAOA phase separator and mixer in the old fashion, simply by alternatingly applying the phase separator and the Grover mixer. So what we are now proposing in this work is to simply discard the necessity of having a uniform superposition. And in the same way, the amplitude amplification algorithm generalizes Grover's algorithm in the sense that it also allows for non-uniform superpositions. We do the same thing with Grover mixer QAOA and therefore name it amplitude amplification mixer QAOA, or short AAM QAOA. And the idea is very much the same. So instead of a uniform superposition, we just demand that our state preparation circuit maps the zero state to some generally non-uniform superposition of all feasible computational basis states. But then the math holds the same. So now I can define my amplitude amplification mixer by the exact same expression, namely I sandwich the identity minus 1 minus e to the minus I beta times the projection onto the zero state between this state preparation routine. And then also define the AAM QAOA in the exact same way. I first apply the state preparation to the all zero state and then alternatingly apply the phase separator and the amplitude amplification mixer. Now, in order to connect that to the previous convergence discussion, what actually holds is if for all feasible bit strings x, the amplitude alpha x of the corresponding computational basis state in the initial superposition is strictly positive, then the amplitude amplification mixer fulfills this stronger mixing property that we discussed before. And therefore, in this case, the AAM QAOA, as outlined here, converges. And then this especially holds for the Grover mixer QAOA. So the convergence proof for this more general framework also covers the Grover mixer QAOA. And now that we talked about the knapsack problem and QAOA, now let's finally introduce the coolest part of this presentation, the quantum tree generator. In order to motivate it, let's look at the decision tree for a knapsack problem. The profit values are not important, so let's just focus on the capacity and the weights. So in this case, it's a 3-item instance with capacity of 3 and weights 3 to 1 for the items. In the decision tree, I just start by having not considered any item, and I can also label that as considering the 0-bit string. So I just didn't look at any item yet. And now I have the choice of either excluding the first item. In this case, I just keep the first bit as it is, or I can include the first item and then I flip the first bit to 1. And now in the second step, I again have the choice of excluding or including the second item. So on the left, this gives me 2 more branches. But on the right-hand side of the tree, I only have one option, namely to exclude the second item. Why is that? Because the first item's weight is 3, the capacity is also 3, so the knapsack is already full. The second item does not fit, therefore I don't really have a choice. And now for the third item on the left, at least, the left-hand side of the tree at least, I have all the choices. I can, after not having included neither item 1 nor 2, I of course have the choice of including or excluding the third item. But also if I only include the second item, I still have 2 choices because the combination of item 2 and item 3, they both fit into the knapsack at the same time. But here on the right-hand side, I can also not include the third item because the knapsack is already fully packed. And now the main idea of the quantum tree generator, or short QTG, is to take this decision tree and to explore it in superposition. But the structure remains the same. The only thing I have to add now is an additional register in which I record the remaining capacity. So now we start with the product state 000 in the main register and the binary encoded number 3 in a capacity register. And now we simply retrace the steps of the classical decision tree, but in superposition. So in the first iteration, I can either include or exclude the first item, and I do that in superposition, and I control the ratios of amplitudes via some rotational gate. Namely, with the amplitude cosine of theta, I don't include the item, and with an amplitude of sine of theta, I include the item. Then in the next step, I want to include or exclude the second item in superposition. And in case I did not include the first item, therefore in the branch where the main register is still in the state 000, I can do that really in superposition again. And I can again control the amplitudes via rotational gate. However, if I already included the first item, I'm not allowed to include the second one. So in this case, I don't want this branching to happen, but I can simply control that by controlling the rotational gate on the state of the capacity register. And since this is updated properly, right, you can see after including the first item, the state in the capacity register changes from 3 to 0 because I subtract the weight. Then I can simply compare the remaining capacity to the weight of the second item. And since 0 is obviously smaller than 2, I'm not allowed to include the second item. And then with the third item, we do it in the same way. So in case there's still space, we include / exclude it in superposition. In both these cases, on the right-hand side of the tree, we again don't branch since we control this rotational gate on the capacity register, holding enough capacity for the weight of the last item. So now in a gate language, what does the QTG do? The QTG consists of n layer unitaries, one for each item. These in turn have 2 components. The first one is this rotational gate, which includes / excludes the item in non-uniform superposition. And very importantly, this rotation, this branching is controlled on the state of the capacity register. So what this notation means is I check the state of the capacity register and I do an integer comparison of it to the weight of the item I wish to include. And only if the state in the capacity register, interpreted as an integer, is larger or equal than the weight, then I actually apply this rotation. Otherwise, I simply do not. The second component is then to update the capacity register, namely by subtracting the weight of the item whenever it is included. So I control on the mth qubit in the main register a subtraction gate on the capacity register, and I subtract from the remaining capacity the item weight Wm. And by this, I really generate a non-uniform superposition of all the feasible states to the knapsack problem. Namely, I apply the QTG to the product state all 0 in the main register and knapsack capacity C in the capacity register, and end up with some superposition over all feasible bit strings together with their remaining capacity. And as long as I don't choose extreme values for these angles theta, such that I actually explore including, excluding items in proper superposition, then these amplitudes are strictly bigger than 0. Therefore, we can conclude if we use the QAOA with the quantum tree generator as amplitude amplification mixer, then this whole procedure converges in the sense discussed before. But now let's look actually what happens in practice, because this notion of convergence, and I put it in quotation marks all the time, really is not a practical one, because I cannot control how deep the QAOA circuit has to be in order to reach a certain precision. Instead, I want to look at the practical performance of the QTG. And in our original proposal, we did not use it as a QAOA mixer whatsoever, but instead we really used it as an amplitude amplification version. And we observed that for the knapsack problem, it can actually perform very well. So here in these plots, you can see the comparison of the QTG to some other algorithms, but most importantly also to combo, which if you remember, and on the first slide, I introduced it as the state-of-the-art classical solver for the knapsack problem. And the details of this plot don't matter that much because this plot is taken from our original QTG paper, not from the one I'm actually supposed to present today. But the main takeaway message is that for very hard but not too large instances, the QTG can, under benevolent hardware assumption, actually outperform combo. So that's a very cool result. And the main motivation of this work I'm discussing today was to find out whether this eventual speed up carries over to the QAOA near-term smaller instance regime. So for smaller instance sizes, it's not so interesting to compare to classical methods because these small instance sizes are easily solved by brute force. So instead, we wanted to compare our QAOA QTG implementation to another QAOA method. And at the time of writing our paper, we regarded this one as the state of the art. It's a proposal by Van Dam et al. And it was also presented at IEEE Quantum Week 4 years ago. And I don't want to go too much into detail here because this talk should rather be about our method than their method. But the short summary is that it is a soft constraint QAOA, and they use this clever technique of replacing the objective function f with f times g, so penalizing infeasible solutions with the value 0. In addition, it is a warm-started approach, so they already do some pre-calculation, pre-computation in order to come up with a high-quality initial state. And then for mixers, they use copolar mixers, where they basically control correlations between items. So now let's finally come to the numerical results. We tested the just mentioned copular QAOA for layer depth from q equals 1 to q equals 10, and our QTG-QAOA with a layer depth of q equals 1. The reason why we did not consider higher layer depth for the QTG-QAOA is simply that the QTG itself, when implemented as a QAOA mixer, requires far more gates than the copular mixer in comparison. However, we can already see that it doesn't really matter what layer depth we choose for the copular QAOA. The approximation ratio quickly drops after reaching 10 items to merely 0.4. And for larger instances, actually the capabilities of our simulator could not simulate it further. But we allow ourselves to extrapolate a bit from these capabilities already that we don't expect very high approximation ratios for large instances. In comparison, the QTG-QAOA was able to center around roughly 0.9 approximation ratio through all the instance sizes, which is quite nice. You can see a slight upwards trend, but we would not dare to interpret an increasing approximation ratio for larger instances here. Now the comparison of the cycle count. So just we took the gate count, parallelized the gates as much as possible, and then counted how many cycles / how many individual layers are there For the copular mixer, this doesn't change really much with different layer depths because the copular mixer itself and also the phase separator itself are very shallow circuits. So those are only mild improvements, while implementing the QTG overall scales linearly with the number of items considered. However, now comes the very sobering result. When compared to the solution that the integer greedy method returns, both QTG-QAOA but also the copular mixer QAOA were not really able to beat integer greedy for larger instance sizes. So where everything is fine until roughly 10 items, afterward it quickly declines for both methods, and we were not able to really obtain better solutions than we would have obtained by running integer greedy. And of course, in comparison, integer greedy runs way faster because I don't have to optimize any variation of parameters. This already brings me to our conclusion. And first, I want to wrap up what we discussed in this talk. First, we introduced the amplitude amplification mixer QAOA, or short AAM QAOA, as a natural extension of the Grover mixer QAOA. Then we outlined a convergence proof for the AAM QAOA. You can read more details about this in our paper. And then proposed to take the quantum tree generator, QTG, as an example for an AAM QAOA. The quantum tree generator itself was introduced by us in another context, more in the context of fault-tolerant amplitude amplification rather than employing it in QAOA, but we showed, at least numerically, that for these smaller instance sizes, it performs actually better than other QAOA approaches for the knapsack. However, and that's the sobering result, is that even QTG-QAOA, even though it performed better than the other QAOA versions, still got outperformed by integer greedy, so therefore is not really a viable method for solving knapsack problems. However, there are several possible future directions one could go. For example, one could simply use the QTG as warm start for other types of QAOA, but then not use it as a mixer, because implementing it as a mixer is very expensive in terms of gates and cycles, and in the end did not yield the best results compared to integer greedy especially. But we could also again step away from the QTG and consider the general framework of amplitude amplification mixer QAOA, but for more difficult problems where we don't have such a powerful classical heuristic, because the framework of AAM QAOA is generally formulated, and also this convergence proof holds for the general case. In parallel, one could, of course, also work further on the classical optimizers that are being used for obtaining the parameter updates, especially since AAM QAOA gives additional guarantees regarding reachability of the optimum. So one could also try to map those guarantees and promises to a more promising classical optimizer. Thank you very, very much for your attention and for attending this talk. I invite you to check out our paper, and in case of any questions or feedback, to contact me or one of my wonderful collaborators via email.